Hi everyone, welcome to the second lesson, and what we are going to do today is we are going to continue um, with the second page of this book. The book is written by Edwards and Penny, and the name of the book is Calculus. So in the first lesson we went through the first page, so what we are going to do today is we are going to continue with the second page, and we'll try to prove each and every equation that we'll be facing with during going through the page. Any equation that we will meet, we will try to understand and prove. So the first thing, okay, let's start from here, which is that most application of calculus involve the use of real numbers or variables to describe changing quantities. The key to the mathematical analysis of a geometric or scientific situation is typically the recognition of a relationship among the variables that describe the situation. Such a relationship may be a formula that expresses one variable as a function of another. For example, so here we are given, it says that the area of a circle of radius r is given by this equation. Okay, let's prove this equation. Let's go to here. Okay, what we are going to do is we will try to prove this equation, which says that the area of a circle is equal to pi times r, radius of the radius of the circle squared. And the way that this equation is proved is the following. Let's say that we're given a circle. Okay, so let's say this is our circle, and there is a six-sided polygon inside it. Okay, so it's going to look something like this. Here, let me actually change the color. Okay, so we have here our six-sided polygon. Okay, six-sided polygon inside it, and so this circle has its radius. Okay, so the radius is r, and what we also can see from this drawing, so we have a six-sided polygon, sides are equal. So this six-sided polygon, if we will join these points, okay, if we will join these points, let me actually change to this one. If we will join these points right over here, okay, we will see that actually we can describe this polygon as a as six isosceles triangles just joined one right next to each other. And in this case, r here is equal to r here, okay, which is r here, here, and here. And let's actually take one of these isosceles triangles, okay, and draw it here, okay, and let's give some definition, not definition, but let's okay, we said that this is r, right? This side is r. We have the height of triangle, so this is the height of triangle, and this is the base, so we call the height with h, and our triangle has the base, let's call it b, so this part is b. So we have six isosceles triangles with base b, height h, and radius is equal to r. We know that the area of triangle is equal to so let's say let's call it A, area is equal to half times height of the triangles times the base, right? And this is true for any triangle. In our case, what we can see is that our polygon is six-sided, right? And it covers this part of the circle. If we will increase the number of sides of this polygon, as this number of the n-sided polygon will approach infinity, it is going to cover almost the whole area of a circle. Okay, so actually there is a very nice demonstration. If I'm not, it's a proof of, if I'm not, a proof of the area of a circle or something like this, yeah. And there's a very nice animation when you are increasing the number of these polygons. I encourage you to check it out. Yeah, it's here. Yes, it is here. You see there's a, let me do this. Okay, so right now there's a six-sided polygon inside the circle, but if we will increase the sides of this polygon, we will see that it's going to, as this n is going to approach infinity, it's going to cover the entire internal part of the circle perfectly. Okay, as this n goes to infinity, it is going to cover the whole area of the circle. And so this is the area of just one triangle here. Okay, one isosceles triangle, this one. Okay, but because of the fact that this triangle, this polygon, as this n goes to infinity, consists of n different isosceles triangles inside it, the area of, because of the fact that the polygon is consist of n different triangles, in this case the area of this polygon, okay, so we can say that the an, okay, the sum of all the small triangles that make this polygon, or we can say that the polygon area is equal to n times 1/2 height time base, right? And or we can say that yeah, I mean, this is probably a very nice representation that so let's say in this case the polygon area is going to be 6 times 1/2 times h times b, okay, because this polygon is six-sided, and the polygon area in this case is equal to this amount. But as this number of triangles that make this circle increases, make this polygon increases, we can describe the polygon area as n infinitely many amount of triangles times 1/2 height time base. And then what we can see is we can see that if we will put this n inside here and write as, so polygon area is equal to 1/2 times h times n times b, n times this small b, n, for example, in this case, 6 times this small, the 6 times the base of these 6 triangles will give us not exactly, but the circumference of the circle. But as we increase the number of these triangles to infinity, as you can see here, we can say that if we will sum all the bases, we will sum the value or the length of all the bases that make these isosceles triangles, we will be able to say that the sum is equal to the circumference of the circle. And we know that the circumference of the circle is equal to 2 pi r, right? And so we can write it as 1/2 times h times 2 pi r, and so this is going to cancel on, and we're left with h times p times r, right? The thing is that as this n approaches to infinity, the radius of the circle and of the polygon is going to be equal, or there's going to be a very 0.000000001 amount of difference between r and h, right? So as this number of triangles going to increase, their area or difference between h and r, okay, is going to decrease. So let's say that when, let's say, n is equal to, I don't know, 1 million, we are left with this amount of small, with these kind of small triangles, okay, and here r is again the radius of a polygon, and here is it's equal to, the height is h. You can see that there is a very high difference, a visible difference between the length of r and the length of h. But as this number of the triangles increases, or we can say number of the sides of a polygon increases, this r is going to approach h, right? There's going to be very small difference between them. So as n goes to infinity, we can say that the polygon area is equal to h, which is going to be r, or the value of not a radius approaches h, but radius of, but this is the same. Yeah, this is the same thing. The height approaches radius approaches height. The idea is that we will now think of height as of r, because there is a very small difference between them. So at the end we can say that height times p times r is equal to r times p times r, which is equal, as this number of n increases, we can say that we can describe polygon area as the area of a circle, which is equal to pi r squared. Okay, I think that, yeah, so we've proved this first equation from here. Just one thing, the formula of the circumference of a circle is proved. It's equal to 2 pi r, right? Or is equal to p times d. What I have found in an internet of the proof of this equation is the proof that is usually given is with the value of pi, which says that this mathematical constant is equal to the circumference of any circle in the world divided by its diameter. Okay, this ratio gives us a certain value which is always equal to the same value, which is equal to the pi, and from here we say that the circumference of any circle is equal to this mathematical constant pi multiplied by the diameter of this circle. Okay, so we are good with two equations. Now we can go to the next one, which says that the volume of V and surface area S of a sphere of radius r are given by these two equations. So the first equation is volume is equal to 4 over 3 pi r cube. Okay, let's prove this equation. In order to prove this equation, let's say that this is our coordinate area, axis of coordinate axis. So here's our y, is our x, and there's a circle inscribed in it. So let's say this is our circle, and there's a radius r, and actually I drew it in a more beautiful way. Yeah, so this is our circle with radius r. So let's say that this is okay, and so this is our sphere with the radius r. So this is our radius, or we can in order to prove this formula, what we do is let's say that we are slicing our sphere somewhere here. Okay, so let's say that we are making a very tiny slice in here. Okay, so there's a tiny slice in here. Let me do this in order to be able to fill it. Okay, so I'm making a slice here, and what I can see is that the length from my origin from here until here is equal to radius again. The radius of this strip, okay, of this circle of a slice is, let's say, is equal to x, and the distance between my origin and this slice is, let's say, is equal to z. What I can by Pythagorean theorem, I know that the x squared plus z squared is equal to r squared, right? Yes. The area of this circle in my case is going to be, so area of this slice circle, let's go like this, is equal to with the radius x, it's going to be equal to pi times x squared, right? So this is the area of my slice circle. What I can do next is write this equation as this one. this one I can write as x squared is equal to the radius of my sphere squared minus z squared, right? And I can plug this one here, so it's going to be, let me change to the white. Okay, so it's going to be a is equal to pi times r squared minus z squared, right? Or it's equal to pi times r squared minus pi times z squared. This is the area of my slice, z value distant from the origin. What I want to do is I want to evaluate this area of infinite amount of slices made to this circle. Okay, and in order to do this, I'm going to integrate this equation for all the values of z, okay, for all the different infinite amount of slices done to this sphere. And again, why I'm doing this is I'm going to integrate this equation. I'm going to integrate this equation, pi r squared minus pi z squared, between 0 and r, but I'm going to multiply to 2 because in the first case I'm doing from here to here, okay, in order to evaluate all the slices between my origin and the upper part of my sphere and the lower part of the sphere. Or the way that I can do it is between minus r and r, but this is just for making the job a bit easy. I'm doing 2 times, I'm dividing the sphere into 2 parts and multiplying by 2. So, and with the tiny change in z, very little change in z, in z. So yes, we can now do the job. So in this case, a is equal to 2 times it's going to be pi r squared, right? Pi r squared times z multiplied by minus pi times z cube divided by 3. Yes, and we can multiply it by 2, so it's going to be 2 pi r squared z minus 2 over 3 pi z cube, and we say that it's going to be between 0 and r, so we should evaluate it in between 0 and r. And sorry, I think that I said this one incorrectly. dz means by taking into account a very small tiny change in the amount of z. Okay, so yeah, we said that this equation is going to be evaluated between 0 and r, so we can just simply put, sorry, it's not area, here when we are integrating it's going to give us volume. Okay, when we are integrating, because of the fact that we are taking into account all the area of all the circles, slight circles, it's at the end the integrated value is going to give us the volume. So this one is going to be volume. So the volume at the end is going to be equal to 2 times pi times r squared times r. So this is z and this is z, where we are going to plug in our r value. So this is r minus 2 over 3 pi r cube, this is for r, and for 0 it's going to be just 0. So we can do just a simple subtraction, so it's going to be 2 pi r cube minus 2 over 3 pi r cube, which is just simply is going to be how much? Okay, so we can write it as 6 over 3 pi r cube minus 2 over 3 pi r cube, or it's just simply equal to 4 over 3 pi r cube. So by means of this, we've proven that the volume of a sphere is equal to 4 over 3 pi r cube. Okay, let's move to the next equation. The next equation is the surface area of a sphere. The surface area of a sphere is the formula for a surface area. Surface area of a sphere, so you know that we are talking about sphere, is equal to 4 times pi r squared. Okay, so this is the formula for the surface area, and now we will try to prove it. Okay, so let's quickly prove it as well. And in order to do so, let's quickly draw. Okay, no, we cannot do this. I want to copy the image, but that's okay. We'll do the a new one. So let's quickly draw our coordinate axis. So this is our y coordinate and x coordinate. This is y, this is x. This is our so let's say this our sphere. Okay, so this is our sphere. In order to prove this formula, let's again consider a very small slice of this sphere, and let's again say that we are interested in this small not slice but a strip of a sphere, which is just a strip which takes a very small surface area of this entire sphere. Okay, and we'll see at the end that by just summing these small amount of surface areas, we will be able to get the surface area of an entire sphere. And in this case, let's say that from here to here, we this distance is equal to the radius, right? Let's call this area right over here again z, and the area of this inscribed circle is, let's say this is x. Okay, and there's also let me quickly look to my notes. Yes, and there is also this this tiny distance, this tiny length of this strip. Okay, and we will call it ds. Okay, this small length of this strip is let's take it as ds. In order to find the area of this circle, okay, of this circle right over here, okay. We just use the simple formula, simple formula of which is so in order to find this small the area of this small strip, the surface area of this small strip, we just look to this strip as a, at least the way that I see it, we are looking at this the area of this small strip as a rectangle, very with a very tiny there's a very long base in comparison with the height. In this case, this length, okay, is going to be ds, and the base or the length of the rectangle is going to be equal to the area is equal to circumference of this circle that is inside it. Okay, so this one is going to be just circumference is equal to 2 pi r, right? So we can say that the area, this small tiny surface area of this small strip, or let's call it dA, is going to be just equal to this the length of this circle, or the length of the rectangle, which is 2 pi r, times this height of rectangle, which is equal to ds. So we got the equation of this small tiny surface area of this tiny strip. By integrating this equation, we will be able to find the surface the surface area of a sphere. But before that, we need to describe this ds in a different way in order to be able to integrate it. And the way that we are doing it is the following. In order to describe ds, we should go to the basics of calculus, okay, some basics. Let's say that we have the graph like this, and this is this small change in the value of the function. Let's call it ds again. So it's this change is described by some change in x value, which is the causes the change in the y value. So there is a contribution of x coordinate, which is, let's call it dx, and the contribution of y coordinate, which is called dy. So this ds can be described as by Pythagorean theorem as ds squared is equal to dx squared plus dy squared, right? Yes. By dividing both sides of this equation by dx squared, we can say that ds over dx squared is equal to 1 plus dy over dx squared, or we can divide by dy, and in this case ds over dy squared is equal to dx divided by dy squared plus 1. What we can do next is, we are again, what we can do right now is we just simply can take ds out, right? And we can write this equation as the square root of in this case 1 plus dy over dx squared times this dx, right? Yes. And the same ds is also can be described as 1 or dx over dy squared plus 1 times dy. And let's move here. Is there anything left? No. So so what we are doing now is we can either take this one or this one and plug in here. Okay, so let's say that we are taking the first one, this one. Let's just quickly do this, copy, and let's paste it somewhere here. Let's quickly paste it. Okay, and we said that the area is going to be this dA actually is going to be 2 pi r times ds. We were able to get ds, so we need to just multiply it here, and here we are. Okay, so what we are gonna do right now is we are just going to integrate it. Okay, let me just so again, what we are doing is we are integrating it from both sides, okay, in order to get the area of the whole sphere, and we are going to do it so in this case it's going to be just a surface area, but we are going to we need to define a specific interval through which we are going to evaluate it, and I'm again choosing 2 times evaluating between 0 and r, 2 pi r 1 plus dy over dx squared times dx. Okay, so I'm evaluating between 0 and r, and I'm multiplying twice in order to evaluate all the surface area of these small strips above origin and below origin. This integration is just a notation that describes the infinite amount of summation in our case of these very little surface areas of these strips. Okay, so this integration is just allows us to do an infinite amount of something. In our case, infinite amount of summation of this surface area in order to get at the end the surface area of the whole sphere. Okay, and we are doing this integration in certain interval because we are, you know, limited with the radius of a sphere. We cannot go out of the sphere, or just do integration until a certain part inside the sphere. We need to take the whole, cover the whole area, the whole surface area, the whole area of the sphere. So we are doing so here we are going to do some calculation, and but before that, let's write it as a is equal to 4 times 0 r, p is constant, you can take it out, radius is constant is also can be taken out. This ends here, it's not inside it. We can write this one as wait, it is sorry everyone, I did one mistake at the beginning. Here we said that the area of this small tiny strip is equal to the area of this circle, this one multiplied by this ds, the height of the rectangle. Here we said that the circumference is equal to 2 pi r. R at the beginning we said it's a radius of a sphere, it's not a radius of this circle. The radius of the circle is equal to x, so in this case it's going to be 2 pi x, okay, and here is going to be 2 pi x, okay. So the probably, okay, we didn't use it here, it's not used here as well, so we can just change it here and here, because I'm looking to the equation and something is not right, but I cannot find what is not right. The idea is that x is changing variable, so it cannot be taken out. It cannot be taken out. It's going to be inside times the square or the square root of dy over dx. Okay, before moving forward, we should do the following thing. We should describe dx with the following notation. So this is our circle, right? Wait. So this is our this is our circle, right? Not circle, sphere. This is the radius of the sphere. This is r, this is x, and this is z, right? X here, so if this is phi, okay, the angle of rotation of the radius, a radius of the sphere at any point can be described by this phi with regarding to x and y coordinate. So in this case, this phi here is also going to be equal to phi here. Okay, we'll just increase this rectangle. It looks something like so. This is r, this is phi. So this angle here is phi. This angle is also going to be phi. This angle is also going to be phi. We have x in here and z here. In this case, cosine of phi is going to be just equal to x times the divided by the hypotenuse. Sorry. So in here we can say that x is equal to r times cosine of theta, or we can say that the tiny change in x, or the dx is equal to r times cosine of theta times d theta. Okay, and we can do the same for what? We can do this for what? We can do this for both x and y, but I described in here y as z, okay? But the idea is that we can describe x as r cosine of theta, get dx, or we can what we can do is we can also say that the z is equal to, okay, let's call this z as y, right? Because this whole equation is driven by y here, to be just to make it easier to plug in. And here is y. So sine of y, sine of theta is in this case going to be y divided by r, or y is equal to r sine of theta, but we will go with x. What else we can notice here is that x squared plus y squared, right? X squared plus y squared by Pythagorean theorem is equal to r squared. We have this one, we have this one, and we have this one. We can also go with this one, but I'm choosing to go with this one. Just simply plugging whatever we have here. We can, okay, we know that the x here is equal to how much? Is r cosine of theta, right? 2 pi goes out, we are left with x. We are saying that x equal to r cosine of theta, square root of 1 plus dy. We said that the dy dy divided by dx squared. I think that I'm doing something wrong, but I don't know what exactly. Okay. Here we said that the x squared plus y squared is equal to r squared, right? So we can simply take y out, okay, and say that y is equal to just a square root of r squared minus x squared, right? In order to represent this part, we are going to take a derivative of y with respect to x, so dy over dx, and it's going to be equal to r squared minus, by chain rule, r squared minus x squared divided by 2 square root of r squared minus x squared, which is equal to minus 2x squared, no, minus 2x, sorry, divided by 2 r squared minus x squared, and this is cancelling out, so we are left with minus x divided by r squared minus x squared. Okay, now we can just simply plug it here, and it's going to be 1 plus dy over dx squared, so it's plus x squared divided by r squared minus x squared. Dx, we said that it's r cosine of theta d theta, r cosine of theta d theta. Then the area is equal to 4 pi evaluated between 0 and r, right? Yes. Am I doing this? 0 r, r cosine of theta, yes, r squared minus x squared plus x squared divided by r squared minus x squared, r cosine of theta d theta. Wait, dx here is, it's r cosine of theta, dx is r sine of theta. I'm sorry, my mistake. r sine of theta. Okay, so in this case here we will have for x equaling to r sine of theta, and here is also sine of theta. So we can again so this one, they're cancelling out. A is equal to 4 pi 0 r r sine of theta, r times r squared sine of theta cosine of theta, square root of dy over dx squared. It is x squared r squared minus x squared plus x squared. Okay, yes, we are in the right way. So it's going to be equal to r squared divided by r squared minus x squared, right? Yes. Times d theta, but when we moved from x's to the radians, one thing that we mixed together is, one thing that I made a mistake in is it would be better to first do all the calculation with x and then plug, instead of x and dx, these values with the theta and change the interval. But I think that we can do it here, but just know that when theta and x here, it's not a correct way to do it. So let's just take this one for now out of it. Here we are going to entirely plug instead of x its value, and we are going to change this interval between 0 and r to 0 and pi over 2. Okay, and so yeah, it's just we are doing it in order to again evaluate upper part and the lower part, but in terms of theta. And the way that it is evaluated between this transition between 0r and 0 pi over 2, one additional way to do it is just put 0 and r instead of x. So in the first case it is going to be how much? So in the first case it's going to be r cosine of theta is equal to 0 at theta is equal to pi over 2, right? And r cosine of theta is equal to 1 is equal to r equal to 0 at pi over 2, and the r cosine of theta is equal to r as theta is equal to pi, right? no, 0, sorry. Cosine of theta is equal to, cosine of theta is equal to 1 at 0 or pi, and the cosine of theta is equal to 0 at pi over 2. So we are changing these 0 and r interval to pi over 2 and 0 interval. Okay, so here we are left with 0, and so if I'm evaluating 0 r, it means that pi over 2 is going to be here and 0 is going to be here. Yes, and then we just continue our calculation. R squared sine of theta cosine of theta, r squared divided by r squared minus x squared. X, we said that this is r cosine of theta, or r squared cosine of squared theta. We can write this part as 1 minus r squared, 1 minus cosine of theta, cosine squared of theta. This one will be gone with this one, and this one will give us sine squared theta, right? And we can then do what? So we can write, I'm running out of space, so I will do, okay, a is equal to 4p between 0 pi over 2 and then r squared sine of theta cosine of theta times 1 over sine of theta out of square root is going to give us power 1. This one is gone with this one. A is equal to 4 pi between pi over 2 and 0. So we can just quickly integrate it. A is equal to 4 pi r squared, so this d theta, d theta, and it's equal to how much? It's equal to it's equal to 4 pi r squared sine of theta evaluated between 0 and pi over 2. At 0 it's going to give us how much? It's going to be 0 minus 1, and a is equal to minus 4 pi r squared. I think that and I made somewhere mistake with, I think this is by okay, let's just quickly, alright guys, the mistake was here. I made this mistake taking the derivative of x. It is minus r times sine of theta, minus r times, so when we were plugging this dx into here, it's going to give us minus here and here and here and here and here. So so here it is going to be minus here and minus here and minus here, so at the end it's going to be plus. So at the end we proven that the surface area of a sphere is equal to 4 pi r squared. Thanks a lot for watching, and I wish you to have a great day.